Welcome to Cinemeric Live, Application Technology Made Simple. Our video series presents Cinemeric topics in a hands-on and concise way. Today's topics: machine integrated workpiece measurement for 3-axis milling. Our agenda for today: we'll take a general look at the Cinemeric measuring functions and then examine the topic of workpiece measurement. And of course, there'll be our hands-on section on a milling machine, the Cinemeric measuring cycles. Let's begin with an overview of the measuring functions. First of all, it's important to point out that measuring on the workpiece is used to define the position and alignment of the workpiece in the machine coordinate system. The main purpose is not to document the final dimensions, tolerances, or dimensional accuracy of the finished workpiece after machining. That's the job of an autonomous external measuring machine. When measuring workpieces, we make a fundamental distinction between two modes. On the one hand, we have the jog mode or setup mode. On the other hand, the automatic mode, also known as process measuring. I'd like to begin by saying a few words about the 0 points of a milling machine. The machine zero is determined by the manufacturer. It's fixed in the origin of the machine coordinate system and cannot be changed. The workpiece 0 point, on the other hand, represents the position of the workpiece within the machine's workspace. The machine, therefore, knows the position of the workpiece on the machine table. And this in turn is based on the 0 point determined on the drawing, or in the CAD with the solid model, or in the DXF model. This also makes it the starting point for programming. It is the universal handling of workpiece zeros that really makes CNC machines effective, because this is what makes it possible to reproduce workflows. There are different measuring tools available for measuring workpieces. These range from traditional, in other words conventional test or measuring methods, to analog probes and touch trigger digital 3D probes. But whatever the method we choose, the aim is always to move or position the milling spindle precisely over a defined workpiece edge that we've determined ourselves. We want to communicate the position and alignment of the workpiece in the machine coordinate system to the control system so that the machine knows where my workpiece is. For the purpose of orientation, we determine an edge, and the center of the spindle is precisely the center of the milling spindle that has to be positioned above the edge. We can use various methods for this procedure. On the one hand, using a milling tool which has to rotate. You move it slowly towards the workpiece, and while it's scratching, as we say, you know, okay, this is exactly the point where the machine or the tool is in contact with the workpiece. This value is transferred by soft key to the machine's control offset. Another way is to use an edge probe. This is flexibly mounted by means of a magnet and spring mechanism and is integrated into a tool holder. The tool holder rotates in the same way as the milling cutter, and while it rotates and approaches the workpiece, we have a mechanism here that runs smoothly when it makes contact. An eccentric movement becomes a concentric movement, and then you know that the spindle center is exactly aligned above the edge. The analog probe is also integrated into a tool holder. The probe is located in the machine spindle, and of course it doesn't rotate, it stays still. And while it scans, it's mounted so that it can move in X minus, Y minus, X plus, Y plus, and of course in Z. You can position it with perfect precision. And you can transfer this value to the offset by simply pressing the soft key. The modern version is the 3D probe. This touch trigger digital probe is very sensitive to touch. When it touches the workpiece, it triggers a contact and the value is automatically recorded. Of course, it's important to note that these digital probes, or touch trigger probes as they're also called, require a pre-fitting, a machine conversion or a preparation of the machine for this digital process. In other words, it's not enough to simply insert the thing into the spindle. It's not as easy as that. You need a transmitter and a receiver to ensure communication between the measuring instrument and the controller. It is, of course, absolutely essential to calibrate probes before using them. Calibration means setting a standard scale for the measuring instrument, or in this case, the probe. And it doesn't matter if the probe in question is a touch trigger digital version or an analog one. In either case, it's extremely important with both the digital and the analog version to ensure concentricity of the measuring tip mounted in the machine. There are various ways of doing this. Of course, you have to carry out the radius calibration or diameter calibration of the ball. This is done using a calibration ring. These calibration rings are available in various diameters. This one has been manufactured to precisely 24.999 millimeters, which puts it in the micrometer range. You place it onto the machine table and position the probe you want to calibrate so that it's above and in the drill hole. A good visual estimate is sufficient. That's all it takes. The procedure is then started using Sinumeric's own calibration menu, and the probe scans various points of the inner diameter. As the ring has a precise inner diameter, and the probe always measures the different value, as it must, it's the calibration ring value that counts. And then the probe and the control system know what the exact diameter is. This also applies to the analog probe, of course. Here too, the concentricity has to be adjusted and the length calibrated. Just like with the digital version, this length calibration is performed in internal or external length measuring systems. This could be an external tool presetter or the machine's internal tool length measuring system. Again, it's worth drawing attention to the calibration conditions. These always have to be the same. In particular, it always has to be in the same plane, G18, G19 or G17. And of course, the feed rates, that's to say the speeds at which the measurements are taken, always have to be the same for the actual measuring process as for calibration. Although the measuring instrument has been calibrated, measuring inaccuracies can still occur. For example, there can be geometry errors in the machine axes, radial eccentricity in the spindle, temperature fluctuations or contamination of the item being measured caused by swarf or residual cooling water, for example. In other words, measuring accuracy depends on the accuracy of the machine and the measuring accuracy of the calibrated measuring instrument. Jog and automatic are two different operating modes. Jog is the setup mode, and automatic is the process measuring, in other words, automatic measuring in an ongoing process. The jog setup mode is used to prepare the machine and the workpiece for machining. The main elements here are, for example, placing a blank in the machine coordinate system, clamping it tight, and specifying this point in the control system. For example, with G54 or G55 or G56, depending on the 0 point you want to use. In other words, the 0 point position in the cutting zone is determined in jog mode. And as I said before, this process is partly automatic. Process measuring means I call up special measuring cycles in the current NC program when in automatic mode, and these are then executed in sequence. For example, you can check the dimensions of a milled pocket, and if it's too small, you can have it corrected automatically. And of course, you can also have the 0 point corrected. This means in jog mode, we have manual or partly automatic execution, and in automatic mode or process measuring while the program is running, we have automatic implementation of measuring cycles. Here's an overview of the measuring functions available in jog mode. All of these functions can be used with a touch trigger 3D probe, but only some of them with a manual probe. Align edge is another very interesting cinemeric function. For example, if the workpiece is not clamped straight or aligned on the machine table, one edge is measured and this misalignment is offset by turning the workpiece coordinate system in the software. In automatic mode, in other words during process measuring, 3 functions are available for measuring a workpiece. One of them is the compensation of the workpiece's work offset. This means, for example, if blanks are fed automatically into the cutting zone, a previous measurement makes sure that the blank is really in its specified position. The second function is the correction of the tool geometry. A good example of this is milling a pocket. When the measuring cycle is activated automatically, the probe measures whether the pocket matches the preset contour or dimensions. If it's too small, the workpiece is made smaller by the respective value, for example. Machining restarts to get the pocket to the required dimensions and ensure dimensional accuracy. The third function is measuring, simple, straightforward measuring, where a measuring log can be output and stored as required by the operator. The overview shows us the options we have in automatic mode for meeting all requirements using a touch trigger probe. And here is the overview of the types of touch trigger probes supported by Cinemeric. Cinemeric also offers the option of logging all the measuring results to make the production process transparent and uniform. Here we have the choice between a user log, a user-defined template that you can customize to your needs, and the default measuring log, which is a ready-made format for every automatic measuring cycle. And each of these output formats is available in tabular form or as a text. Our practical section will demonstrate how all that works in detail. Here we have our workpiece clamped in the vise on the machine table, but the control system, or the machine, doesn't yet know where it is within the coordinate system. Now we have to set the workpiece 0. I'll just put it in the middle of the drill hole. It can also be at any other point, regardless of where it's specified in the drawing. Now we're going to move the 3D probe to the spindle on the machine tool. Next, the 3D probe will be positioned above the drill hole where we want to specify the 0 point. All you have to do is move it approximately to the right position in the hole. There's a measuring or safety range that can be adjusted flexibly, of course, so that it doesn't begin to measure exactly at the edge, but is first switched into the measuring feed rate. Now it's important to set the measuring mode you want to select. In this case, we want to measure a drill hole. Here we set the approximate diameter of the drill hole and the 0 point we want to specify. In this case, it's G54. You also hear the acoustic feedback when the measuring ball touches the sidewalls. That's the measuring procedure, and here is the active G54 work offset and the corresponding parameters of what was measured. Now the 0 point is specified in the offset under G54. In automatic mode, in other words process measuring, we've inserted the measuring cycles and the log of the measuring results into an existing NC program so that the measuring operation runs automatically after machining. In this case, we want to finish a circular pocket to a specific diameter, in this case 32. This has been done and a forced stop included after milling was completed. That is command M0. In other words, when the control system encounters this command, it will definitely stop. That's because after machining and before starting the set automatic measuring process, the component has to be freed from swarf and any cooling water. The program structure looks like this: program header, the actual milling or drilling operation, the M0 command that ensures a stop. The next step is the setting for logging and outputting the measuring result. It's activated once and either displayed here in the visualization mode for 8 seconds after the measuring operation, or it's displayed on NC Start, or when there's an alarm. We can select either the default measuring report or a user-defined measuring report, and a new measuring document can always be added or an attachment added to an existing measuring document. This is where we specify where the measuring log should be stored. In other words, we specify the file path. Here we can also save the measuring log on the server or any other place. To do so, please assign a unique name. Then comes the command for calling the measuring cycle. In this case, the tool is our 3D probe. Here the default measuring method is the position where the drill hole is situated in X and Y. In this case, it's 0, 0. In other words, our workpiece 0. Here is the measuring depth, in other words, how deep the probe should be immersed into the drill hole to be measured. And here is the diameter set point that's being measured. Now the component is cleaned. Then we continue with execution of the program. After cleaning, close the doors, go back into automatic mode and press Start to continue the program. The probe is automatically placed into the spindle and automatically starts the measuring operation. Here too we get acoustic feedback, 4 probings of the inner wall of the drill hole. Once this has been completed, the measuring operation is automatically displayed for 8 seconds. We can see that we have a tolerance of 1.2 hundredths of a millimeter. Then the program continues automatically. In our case, we've reached the end of the program. Now we're in the Program Manager, in our program directory. And we can look at this measuring log for longer than 8 seconds because it's saved as a text file here. We see here the diameter should be 32 but as I said before, it's 1.2 hundredths smaller. This is either within or outside of the tolerance, depending on the tolerance stated on the drawing. The wide range of cinemeric measuring cycles for milling operations meets all the requirements a user can place on a modern manufacturing environment. These include benefits such as time savings thanks to shorter setup times, uniform input support, that's to say, the measuring cycles work exactly the same in shop mill as they do in the program guide, and the realistic display of the measuring process in the cinemeric simulation works in exactly the same way as the machining process. And last but not least, there's the easy creation and output of measuring logs. Thanks for watching, and see you next time.
Siemens, ingenuity for life.